Hi, welcome to the sixth lecture on compactness. We will continue with our study of compact subsets of a topological space. The main result of today's lecture is a compact subset of a Hausdorff space is closed. You may remember we proved in a metric space, if A is a compact subset, then A is closed. We also proved A is bounded, but that boundedness is a concept available only in the metric space, not in general topological spaces, right? So only in a Hausdorff space a compact subset is closed. Okay, so that means there exist topological spaces in which a compact set need not be closed. Okay, we will give example of that also, right? Okay, let us get started. Okay, yeah, so this is the title, compact subset in the topological space. Is actually sixth lecture in compactness series, which is part of topology. You have my email ID and reference as in compactness 1. My YouTube channel is youtube.com/c for channel /Kumarichi. That's the name of my channel, right? Okay, let us do. So suppose K is a compact subset of this, okay, and A is a subset of K. Does that imply A is compact? No, because we know this is compact and this is not compact. Okay, but what we have is a very interesting result. Let me call it as a lemma. Let X tau be a compact space. Okay, let K in X be closed, then K is compact. Understand this? So in particular, if I have a topological space and if K isn't compact and if A is a subset and suppose A is closed, subset of this, okay, A is closed here, closed in X tau, then this will be compact. Okay, so A has to be closed in K with the subspace topology. Okay, let me take this out. Yeah, right. So proof is easy. So I want to prove K is compact, right? To prove a closed set, the closed set K in X tau, this is a compact space, this is compact, right? So that what does that mean? You are going to give me an open cover of K. Now remember what kind of open cover I need. If you looked at our earlier examples 2 lectures ago, and also the fact that K is a closed set in X, right? So that the hypothesis K is closed in X must be used. Therefore, what kind of open cover I should work with? I should work with open cover of finite type 1. Why? So let Ui I and I be an open cover, okay, of type 1. What does that mean? That means Ui is open in for all I, Ui is open and K is a subset of union Ui, right? This is what the meaning, right? Now what is the hypothesis? Hypothesis X is compact. So what do you think I should do? I have to see. Now again, look at the picture. You know, having a picture will always help. Let me do that. This is my K and this is my X. Okay, now I have open covers. Okay, these are my ui's, right? So my hypothesis x is compact. Therefore, what should I do? I should get an open cover of x. But I want to extract a finite subcover of ui for k. So my open cover of x should involve ui's also. Do you understand that? So what is a very natural thing? Whatever is left over, I should cover. See, already this much is covered. More than k is covered, right? So the leftover things what I have to cover. So how will I do that? Let's look at u to be x minus k. Now what do I know about k? K is closed, therefore this is open, right? Now how many of you see this? ui, I union singleton u, this is an open cover of x. Right, so what is the open cover? Just to, if you want me to write a picture, it will look like this. All these fellows will form the open cover. Everything outside k. Right? Okay. This is very clear to all. Very good. Now what do I know? So since x is compact, this is clear because x equal to k union x minus k, but k is contained in union ui, I, and this is same as u, this is same as u, but this is all subset of x. Therefore I found x equal to this. Therefore x equal to this. Yeah, therefore it's an open cover. Since x is compact, there exists a finite set F which is contained in I and union this singleton u. Okay, I'm just going to do this itself, right? So let us say there is a finite subset F such that, okay, x equal to union I of u of union u. It's a finite set, right? Finite subset of this collection. Which collection? This collection. Okay. So what is possible is that collection contains u or not contain you. You understand that? Yeah. But in any case, I can always add u to that. You follow that? This finite collection may be some uj, j in j, so that this is contained in ui, I in I, and union u, right? So my u, this is j is finite. My u may be there or may not be there. Yeah, right. Are you following? Okay. Well, you can treat both the cases separately, but I'll just try to do it this way, right? Suppose let us say u is not in this finite collection. Okay, this is a finite set. Suppose not. That means what? X equal to union ui, okay, I in f, and f is a finite subset of this, but this is x minus k. This would mean k must be empty. Yeah, right? So let us write x equal to union ui I in f union u. Okay, now what is that I want to say? I want to claim my k is a subset of union ui I in f. Yeah, why it should be true? Because if you give me an x in k, okay, therefore that means x is in u, sorry, x is in x, that means x is in union ui union u, right? And because x equal to this, right? So if x are not in this collection, then x must be in u, but u is nothing other than x minus k, That's a contradiction. You said x is in K, x is not in K, right? Therefore K is actually a subset of this. Are you following? A contradiction. Therefore give me any x in X, x belong to union ui I in J. I in what did I write? Sorry, J or F. I again get confused. Yeah. Okay. Yeah, here's a union I in F. Yeah, right. That's correct. You follow that? Therefore, ui I in F is a finite subcover. Okay. This implies K is compact because you gave me any open cover of type 1 for K, then I produce a finite subcover. Okay. Pause. Review. Proceed. Second result, okay, is if I have, let's say A1, A2, AN, these are all compact subsets, then A, which is a finite union of compact sets, I equal to 1 to n, is again compact. Okay, the proof is again easy. Yeah, let us just stick to A union B. A and B are compact subsets, right? Suppose I have a collection UI, I and I. This is a type 1 collection, type 1 open cover for A, and Vj, J in J, type 1 cover for B, right? Now let's look at this union UI, I in I, union Vj, J in J. This is an open cover of type 1 for A union B, correct? Because A is contained in union A, B is contained in union Vj, therefore A union B is contained in union of UI, union of Vj, right? Okay, good. Now what do I know? Since A is compact, okay, there is a finite subset F1 of I, finite set, so that A is contained in union UI I in F1, and similarly B is contained in union Vj, J is in F2, where F2 is finite subset of J, right? Therefore A union B is contained in union UI I in the finite set, union Vj, J in the finite set. Okay, so therefore given, okay, yeah, but this way of arguing is wrong. This argument is very naive. You understand that? Why it's naive? That's because I want to prove A union B is compact, right? Therefore, you are going to give me a collection UI, I and I, so that this is type 1 cover for A union B. Then I ought to find this finite subcover. Right? Now let us look at this union I and I is said that this is contained in UI, and similarly B. Therefore, UI is a type 1 cover for A as well as for B. Therefore, there exists a finite set f1 of I such that A is a subset of ui I in f1. And similarly, there is a finite subset. This is why? Because A is compact and B is compact. You understand? Therefore, there is a finite subset f2 of I such that B is contained in union uj j in f2. Now let's look at f1 union f2. See, notice that f1 and f2 may have their intersection. Okay, they may have common elements, but that doesn't matter since f1 is finite, f2 is finite. This is finite, right? And also it's clear A union B is a subset of union I in f of ui. Because you give me an x is in A, in that case there is an I in f1 so that x belongs to ui, but that I is in f1, therefore I is also in f, therefore x belongs to this. Similarly, if x is in A union B, x is in B, there exists an I in f2 so that x belongs to ui, but that I is in f2 and hence it's in f, therefore that x belongs to union ui, I varies over f. You should go through this kind of argument, okay? Otherwise, many of you, because of training, you may simply try to memorize. Please don't do that. So we have proved the result. What have we proved? We have proved union of two compact sets is compact, and by finite induction or union. If you give me a1 a2 an, then I'll have like this f1 f2 f1 finite subsets of I, and take f equal to f1 union f2 union fn, finite union of finite set, therefore f will be finite, therefore my a1 union a2 union an will be contained in ui I varies over f, varies over f. Yeah, the same proof. Is it okay? Right. Now I want to prove intersection of open sets. We have proved union, so the next question is intersection. Suppose A and B are compact subsets of X. Let me just make sure how recording is on. Yeah. Then A intersection B need not be compact. But if A intersection B is a closed subset of A or it's a closed subset of B, it will be compact. That we have seen. Any closed subset of a compact set will be compact. Okay. If I take A intersection B, if it's a closed subset of A, since A is compact, it will be compact. Similarly, if I assume A intersection B is closed in B, then since B is compact, A intersection B again will be compact. No problem. But in general, I do not know. You follow that? Let us look at an example. So let me start with the n with a discrete topology. Okay, right, discrete topology. Now add two elements. One is a happy phase, another one is a sad phase, right? So my space X is going to be n union happy phase union sad phase. Right, now I have to define a topology, right? So I say you belong to, I want to define a topology, define tau on X as follows. Okay, you belong to tau if and only if u is a subset of n, that's it. Remember, it's a discrete topology, therefore it will be open, right? And if either one of them, sad phase or happy phase, belong to u, then the other also belong to the. What does it mean? If this fellow belong to you, if and only if this fellow belong to you, that's it. Okay, so I leave it to you to check this topology. You understand? And notice that tau is not Hausdorff, because if you take any m and n, m not equal to n, they are in n, then what is the singleton is open, singleton is open. Remember that any subset u of n is open. Okay, so every subset u of n is open. There, because it is I want it, right? Therefore they can be separated. So what are the things which cannot be separated? This one, these two fellows cannot be separated. Why? Because the moment one of them belong to you, then this other fellow also belong to you, right? So this is not Hausdorff, right? Very good. Yeah, I wanted to say something, and x minus u is finite. Okay, I forgot to say that. So let me say, so I have a subset u of x. Okay, this is open, that is it lies in tau if one, either u is a subset of n, any subset of n, or two, if one of the faces lies in u, then the other lies in, if only if the other face also lies. And this is finite. Okay, I forgot to write it earlier, right? So you need to check this is a topology. Okay, and it's also not Hausdorff, that we had already seen. Okay, now let's look at this thing, n union third face. This is my set A. And similarly look at n union happy face. Both are compact. Why? Suppose ui is an open cover, right, of A, let us say, then my third face has to be in some uj, right? Now of course this implies happy face will also be there, but most importantly x minus uj, this is a finite set, right? And remember, in uj happy face also will be there, therefore this will be a finite subset of natural numbers, right? And therefore there exists, suppose there is a called a finite subset f of n. Okay, so for each n f there exists ui in in I, so that n belong to uin. If you want, you don't like n, write it as x, right? Are you following? Therefore this collection uj along with uin as n varies over f, this is a finite subcore. And similarly B is also compact. Okay, now what is the intersection B? This set of natural numbers. Remember, A contains only one of the faces, not the other face. Similarly, B contains only one of the faces, not the other face. Therefore, I take intersection, I get all natural numbers. Alright, now let's look at this collection. These are all type 1 open sets, and okay, this is another open cover of n which has no finite subcover. Therefore, what do you think I have proved? So this is not compact. So pause, review, proceed. So I have produced an example of a space which is not Hausdorff necessarily. You will see why it has to be non-Hausdorff anyway. Okay, so that there exist two compact sets, but their intersection is not compact. Yeah, all right. So now let us go to the next one. So this is a theorem. As I said, this is the main result of this. Okay, let x tau be a Hausdorff space. K in X compact. Then K is closed in X tau. Okay, we had already seen the special case of this. If X is a metric space, naturally it's Hausdorff, and we have seen in any metric space, any compact set is closed, and extra condition, a metric condition, namely it's bounded. Okay, now before going to the proof, what are the applications? Suppose A and X, let us assume X tau is Hausdorff, and A and B compact sets. Subset. Then A intersection B is necessarily compact. How many of you can see that? Okay, since A is compact subset of a Hausdorff space, what do I know about A? A is closed. Similarly, B is closed, and finite intersection of two closed sets is closed. This is closed. Okay, but a closed subset of a compact set is compact. You understand? Can you go through the argument? A is compact, therefore A is closed, and B is also closed, and hence A intersection B is closed. Right? Now A intersection B is a closed subset of a compact set, namely A or namely B also, and hence A intersection B is compact. Do you see the logic? Pause, review, proceed. Now the second application is the so-called a part of Heine-Borel theorem. Okay, it's actually, it gives a Heine-Borel theorem for all. Notice that in any metric space we have proved, if K is a subset of X is compact, then we said K is closed and bounded, right? And we also know if, we also know a closed subset of any compact space is compact set is compact, right? Keep that in mind, right? Now we have proved A, B closed and bounded intervals are compact, right? Now suppose A is a subset of R which is closed and bounded. Okay, then I claim A is compact. Okay, we have to prove this. Yeah, now since A is closed and bounded, that means since A is bounded, there exists an M positive so that for all X in A, mod X is less than or equal to M. That means X lies in minus M to plus M, right? But we know this is compact because it's a closed and bounded interval. Therefore, A is a subset of minus M to M, and we know this is closed. Closed where? In R, right? Therefore, this is a closed subset of this. Yeah. Of the compact set, right? Therefore, A is compact. Okay, have shown. So what have we proved? So we already know in any metric space a subset, if A is compact, then A has to be closed and bounded. In particular, if A is a compact subset of R, it has to be closed and bounded as a special case. Do you understand? Now what have we proved? We have proved the converse. You give me any closed and bounded subset of R, then A is compact. Therefore, what you have proved is the so-called Heine-Borel theorem. The usual topology is compact if and only if A is closed and bounded. Notice that in a metric space we already know a closed and bounded set need not be compact. This is something special with respect to R. Okay, so these are the things beginning students should again and again go through. Do not get confused. In any metric space, a compact set must be closed and bounded, and a closed and bounded set in a metric space need not be compact. But in R, a set is compact if only if it's closed and bounded. Okay, please go through all these things. Okay, now let's go through the proof of the theorem. So K is X. Okay, what do I want to prove? It's a, this is Hausdorff space, and this is compact. Then we want to know K is closed, right? Okay, now let again look at the picture. I hope I will be able to draw a much better picture so that it will be convincing for you. This is my X, okay, and this is my K. Right. So for what do I have to prove? I have to prove X minus K is open. That means give me any X not in K, there exists an open set U in tau, so that X belong to U and U intersection K is empty. Therefore, let us look at this picture. I have an X, I have an open set. Okay, I have an X, there I have an open set, I have an X, I have an open set. Okay, which is completely contained in the complement. Yeah? How am I going to do that? If you had followed all my earlier lectures, this was one of the cases we looked at. What did we look at? If A is a subset of a Hausdorff space, okay, a proper subset, okay, how do you generate an open cover using the data? Right? Oh, don't worry, go slow. Right? Let me look at the picture again. I want another picture so that life will be easier. This is my X. This is my K. Right? Keep that in mind. Now suppose you give me an X. Okay, not in K. This is fixed set. Okay, fix. So what I have to do? I have to find an open set U in tau such that X belong to U and U intersection K is empty. Okay, these are to prove all these things. Okay, right. Now let's look at that. Now, since K is compact, somehow I have to get an open cover. Right? Now remember, the whole thing is taking place in capital X because my little x is a point outside K but in X. Alright. So what kind of open cover I should use? Type 1 or type 2? You see that? Naturally, type 1. Now you start with any Y here. Let me use a different color scheme for each one of the thing. Suppose I have Y here. Right? Now Y is in K, X is outside K and the space is Hausdorff. So what do I know? I know there exists an open set U containing X and open set B containing Y so that U intersection B is empty. Don't worry about this U. Okay, forget this U. You follow that? I am going to give a thing. So let me use, this is my open set U and this is my open set B. Yeah, but see as Y varies, I am going to change open sets. Therefore let me call this as By and this not as Ux but I will call it Uy because X is going to be fixed. For each Y I am going to get a different open set containing. Just look at the picture, you will understand what I am trying to say. Okay, suppose now this is my Y, then I will have an open set here and I may have an open set. Okay, so I will call this as Vy, this as Uy. I am using the same Y, do not get confused. If you want, call it Y1, Y2, Y3, etc. Are you following? Now suppose I have a K here, right? So I have an open set here and I have an open set Okay, this will be my Vy and this may be my Uy. You follow that? If you want, call this as y1 1 and this is 2 2, this is 3 3, etc. and so on. So what do you think I have finally done? This is what I have done. Okay, fix x not in k. For every y in k, x is not equal to y. Therefore there exists open sets where in tau, in x tau, so that x belong to x, there is open set uy and vy, so that x belong to uy. Okay, remember it's not ux, and y belong to vy, and such that uy intersection vy is empty. You follow that? So now for each y in k, okay, I have a color open set uy. Therefore this collection uy, sorry, vy, y in k, this is type 1 cover for k. Do you understand? Because for each y I have an open set which contains that, and this vy is open set in x because of Hausdorff of x is what we are using. Is that okay? Now what do I know? I know k is compact. Therefore there exists a finite subset f of k, so that k is contained in union vy, y is in f. If you want to call vy1, vy2, vyn. If k f equal to y1, y2, yn, you can write it vyi, I equal to 1 to n. But usually I avoid enumeration because there is a natural order, it may not have happened. Anyway, is that okay? So now how do I find an open set which containing x which does not intersect k? I am going to find an open set u. Okay, I want to find an open set u so that x belong to this and u does not intersect this. Okay, we are going to exhibit this. So in particular, since k is contained that, it cannot intersect k. Are you following? Now look at the picture. You should suggest. Remember, each uy as y varies over k. Each uy as y varies over f is an open set. But how many elements are there in f? F is finite, right? Therefore, you should be able to think of an open set which contains x. Each open set ui as y varies over f is an open set containing x, and f is finite. Yeah, right. I'm sure many of you should have thought of it, right? So set u equal to intersection of ui, y varies over f. Remember, since f is finite, this will be an open set. Since x belongs to ui for each y, x belongs to this. Therefore, u is an open set containing x. You follow that? Now I claim u intersection union of vy, y in f is empty. Why? Because suppose z belong to this, right? Then z, okay, z belong to u. This means z belong to uy for each y in f. Do you understand? And z belong to union vy, y in f. That means there exists a y dash, call it y naught in f, so that y belong to, sorry, z belong to vy naught. You understand? Therefore here z belong to uy for each y in f. Therefore in particular z belong to uy naught, right? Yeah, therefore what do I get? Z belong to uy naught intersection vy naught. But remember, for a given y naught, how did we choose our uy naught and vy naught? They don't have any point in common. You understand? So this is empty. So this is a contradiction. Okay, therefore what I have shown, okay, so U intersection union Vy Ynf is empty, right? But remember, K is a subset of this, therefore U intersection K, which is a subset of U intersection union Vy Ynf is empty, right? Therefore U is an open set containing X such that U lies in X minus K. So this set is open. That means, so for each X in X minus K, there is an open set so there exists an open set U such that X belong to U and that is containing X minus U, X minus K. Therefore X minus K is open or K is closed. Yeah, so pause, review, proceed. So go through the proof. The proof is very geometric. It's actually simple proof. I tried to explain slowly and explain, okay, that's why it may be a little more intimidating. Sometime a short proof may be useful, I don't know, but please go through it. I hope you like it. We'll meet again.